Welcome to episode 2 of our virtual series on decoding AI and hydrology for water management decisions. I'm Eliza Hale, and I will be presenting this part with my co-host, Laura Reed. Let's dive into it. So today, what we're going to talk about is machine learning models versus conceptual models. In our last episode, we gave an overview of machine learning, and if you haven't seen that, make sure and go back to watch that before you watch this one. If you're in the world of modeling, you've probably heard this quote by George Box: all models are wrong, some are useful. And the idea behind this is anytime you're trying to represent the natural world, a model is going to be an oversimplification. It's not going to capture all of the complexities of the system it represents. However, a model can capture useful parts of the system and provide us with information that can help us make better and more informed decisions. Physical models like the Sacramento soil moisture accounting model pictured here have been used for decades, and they continue to provide value to the field of hydrology. They are, however, imperfect. They were designed in an earlier time before we had access to the compute power and large amounts of data that exist today. And that is where machine learning comes in. So, what are some of the strengths of machine learning? Where is machine learning a useful model to use? Machine learning is great for problems in which there's a lot of data available, in which accuracy is important, and where the relationships between the inputs and outputs in the system are complex. Streamflow fits this very well. So, to understand some of the differences between machine learning models and conceptual models, I'd actually like to start by talking about some of the ways that they are similar. In both machine learning and conceptual models, you can think of the process of getting the model ready as broken down into 4 steps. You start with the inputs and observations of your model: meteorological input, stream flow, snow cover, etc. Next, you select a model that's appropriate for the problem at hand. After that, you tune the parameters of the model. And then there's a little bit of iteration, some evaluation to see how well your model is done, going back and retuning the parameters to make the best model you can. Some of the differences between machine learning and conceptual models are highlighted here. In machine learning, the model is specifically designed to be able to handle large amounts of data. So you can train a model not just on a single basin, but on hundreds or potentially thousands of basins at a time. In a conceptual model, the physical relationships in the system are explicitly represented in the model. Whereas in a machine learning model, the model learns the physical relationships through the parameter tuning. And finally, because machine learning models are built to handle large amounts of data, can be trained on many basins, that means they can make forecasts or make predictions at hundreds of different basins, which is what is one of their advantages. Laura, over to you.
Great, thanks, Eliza. So taking what we learned about the architectures between conceptual and machine learning or statistical models, how do those translate into benefits, limitations, strengths, and weaknesses of each? So we've got a couple of summary boxes here of highlights from each of those. In conceptual models, what's nice about them is that we can relate to them as humans. We know that folks have gone out and measured soil and understood how water can move through that, and then we can write down an equation and assume some parameters, and that makes sense to us when we see those in a modeling framework. The challenges with those are that those parameters are actually really difficult to estimate everywhere, and when things change, those models need to be recalibrated. They need new data to kind of replace the static assumptions within them. If we think about modeling as a spectrum, then on the other side, statistical models, which one example is machine learning models, are data-driven. So you do need data to have the model learn and understand the particular patterns or theories or processes that you want it to. At the same time, when you have a lot of data, you can build in relationships and patterns that aren't physically plausible. And so they're prone to these false correlations, and they need to be constrained properly so that they are predicting and simulating the things that you're looking for. So if you go to the next slide, what we think of as limitations as scientists, I think we can all relate to this, is an opportunity. So at Upstream Tech, we build neural network models for our streamflow predictions, and the things that those models are limited in are the places that we do research. So for example, there is a disconnect between a machine learning and how it learns and the states of the model from what we understand in the physical world, but we can open up that understanding by running different internal tools like this one here showing, it's called input importances, which basically allows us to understand what the model is paying attention to, what inputs are driving the predictions. And so we can understand those inner workings using tools and building these into our prediction systems. So with 2 episodes down, we have 1 left, and that episode is going to focus on machine learning and hydrology in the literature, and then how we at Upstream Tech have taken that science and those advancements and built HydroForecast, our streamflow forecasting service. Stay tuned.